Thank you very much for inviting me here. I'm sorry I cannot participate in Riga on site, but I hope to come at a later time. And it's been a very interesting program so far. So I will share some of our work that we do on astrophysics, the laboratory work, and coupled to atomic structure calculations that we do for astrophysics, and primarily for stellar astrophysics, and also recently for kilonova astrophysics. So I will briefly discuss that. And first I will want to also place thanks and gratitude to all my collaborators. So I'm in Malmö University. It's close to Lund University, and between Lund University and Copenhagen. So we are a handful of persons doing laboratory spectroscopy, but also Professor Per Jönsson, who's heading the atomic structure calculations using the GRASP code, for example. And the work I will describe is focused on experiments, but our aim is to combine the calculations and experiments to provide atomic data for astrophysics. And some of the work is on metastable levels and forbidden lines. That's done in collaboration with the Stockholm University group around Desiree, and also together with Uldis Bershins and his group from Latvia University, which is a very fruitful collaboration and very encouraging, I think. I enjoy it very much. And then I show some lifetime measurements that we heard about the Lund Laser Center earlier by Sune Svanberg, and there are Lars Engström and Hans Lundberg, who have been major players in this work, and also the group in Spain with Teduca Belmonte presented yesterday a similar work, but we work very closely. And of course, we're very grateful to the Swedish Research Council who have funded us for 3 PhD students over the last 10-15 years. So, if you might fall asleep, I'll start off with the conclusions so you can bear this with us. So the aim of the program is then to provide a good set of data. It should be accurate and it should be broad, so it has a range in wavelength, line strength, and excitation potential, and it should also have realistic uncertainties. And the uncertainties are important for the astrophysical applications, not only to get the line data, but also to get uncertainties to provide then the boundaries on the chemical abundances that are derived from these applications. And I mean, the aim and the goal is that these measurements and the calculations, they can provide the data for the astrophysical observations, which are usually taken at a very high cost, using space telescopes or ground-based telescopes, which are very costly. So, I mean, as discussed earlier today, these data are not very costly, but they can really enhance this astrophysical data. So for the stellar abundance studies, I wonder if you can see my pointer.
Yes, we see.
Okay, great. So, I mean, the big question that I want to ask her or to respond to is when and where were the chemical elements formed? So that's the main goal. That's the very, I would say, a high-stake goal, that we're not gonna respond to that one. But we're gonna provide some of the bits. So the question is answered by modeling and also observations. So galactic evolution models of the galaxy, and then observations and the modeling of individual stars. And then here you see the solar spectrum with all the spectral lines taken by the Kitt Peak Observatory. And then what we need to provide the atomic data and the atomic processes that's needed in the stellar models. So that's our aim, the radiative data, which is fed into compared to the theoretical spectrum. So this is for the stellar atmospheres. For the kilonova, as you might know, so the kilonova is an eruption. We've seen only one real kilonova explosion, but that was in 2017. And the kilonova is when a binary star, 2 neutron stars, merge in a binary. And in the merger, there is a giant outburst of light and particles. So these have been observed in this so-called multi-messenger observations. So it's both a gravitational wave, which then can constrain the parameters of the neutron stars, and as an optical spectrum, which then can derive the parameters of the explosion and also the later, this which is called the kilonova, the afterglow spectrum. So atomic data is needed in two different sets, two different times here. So the first, to model the light curve, and here's the light curve. So it goes from top to bottom in different magnitudes. So you can see that the light curve evolves during the first days. This scale goes from 0 to 5 days. And to model this, you need opacities. That is more not particular line data, but broader opacities for basically every element. So that's one thing. And the other thing is detailed data. That means detailed line data with wavelength and intrinsic line strength for each particular element. And this is needed for the afterglow spectrum, which then comes the weeks after the explosion. So after the merger has appeared, then the radiation transfers through these expelled shells. And you can see the evolution of the spectrum, which goes from a more blue peak here. So this scale is from 0 to 2.5 microns. And the peak evolves as it goes down. And you can see that the blue peak disappears and you get more and more red and infrared radiation. So to model and all the elements, the heavy elements which were then thought to be produced in this merger are then expelled, and that can be seen as spectral signatures in this spec. So this is the other set of atomic data. And in this case, you really need accurate data, not so much the wavelength, but also the oscillator strength of these particular lines. And then with this modeling, then you can provide the chemical yields of these events for the chemical evolution. So looking at the periodic table, but labeled as the cosmic origin of the different elements. You can see the blue squares for the Big Bang fusion, and also then the yellow, which are the exploding massive stars. But then for the heavier elements, in this diagram, you see that the purple ones are thought to be merging neutron stars production. So these are the elements that we want to study. And of course, you cannot take all of this at the same time, but pick certain elements which are important, and also which then includes the rare earth elements, but then also to distinguish between these other elements which are from the dying low mass stars, like the yttrium and scandium and lanthanum and such. So, and what is the benefit and the problem with the near infrared observations? So I'll show a picture of this of the Eagle Nebula. This is taken with the Hubble Space Telescope in visual and visual regions, and you can see these three dust pillars. If we look at the same image in infrared, this is what you see. So you can see that the dust gets transparent to this infrared light. You can also see that a lot of stars emerge in the background here. So clearly, if we look at the infrared wavelength region, it's beneficial to see more stars which are at very distant places and in distance which are obscured then by dust. For example, if you want to look at stars close to the galactic center, or stars at very high distances. The other reasons for looking at the 1.5 microns. So apart from the extinction, the atmospheric transmission bands are in the infrared around 1 micron, 1.6 micron, and so. And also, if you want to look at cool stars, they have a lot of radiation in the infrared, which you then can look for. And as a consequence, a lot of the coming astronomical observatories are designed for this region. Some are designed for the 1 to 2.5 microns, and or 1 to 5 microns, like the VLT, the Cryo-RES Plus, for example, and also the Gemini telescopes have infrared spectrographs. However, the atomic data base above 1 micron is sparse. And this is for reason that no one was really interested in the near infrared in the 80s or early, because this was an inaccessible wavelength range. There were no telescopes observing this range, and thus the atomic data was not interested. So despite there being no atomic data in the database, this is a really important region to study. So we've been working on this for the last years, and we will continue to do so for new elements. Also for this, for the kilonova spectra, as you could see, also very prominent in this 1 to 2.5 micron. And from an atomic spectroscopy point of view, what are the near infrared atomic transitions? Well, it's usually, I mean, you think of the near infrared atomic transition as high excitation transitions, high up in the system where the atomic levels get very close. You get these near infrared transitions. But in some of the complex atomic spectra, I will show some examples from scandium, yttrium, and lanthanum. You can get lower excitation transitions, which means that these lines will appear stronger in the spectra in the near infrared. And also, if you go to the heavier elements, if you go to, due to the different configurations going up and down, if you go to the rare earth elements, some of these third spectra show resonance lines in the near infrared. Usually, if you think of an atomic spectrum, if you go to higher ionization, then you will move into the UV. So for example, the iron group elements, if you go to double ionized, they will appear shortward of Lyman alpha, the resonance lines. Whereas if you go to the rare earth elements, some of these configurations shift places, so they will be near infrared resonance lines. And that's also one of the reasons that they will show up very strong in this kilonova spectrum. So I'll take a few examples. We first look at the iron group elements. You can see that this is the partial energy level diagram. You have the 4s transit levels and the 4p levels here. And all the resonance lines will appear in the blue region around 3000 angstroms. So the infrared transitions appear up here. And the excitation energy will be, say, 5 electron volts. These lines will appear very weak. If you go to the other set of elements, like these p elements, this is the same case. And if you look, for example, at silicon 1, the near infrared regions of 1 microns, there will be transitions between, say, 5s to 5p or 4p to 6s up here. So they will also have a very high excitation level energy, whereas the resonance lines don't show up in the optical. However, if you look, for example, at scandium, yttrium, and also lanthanum, so from an atomic structure point of view, these might produce strong near infrared transitions. So for example, you can see at 1.5 electron volts, there is transitions, say around 1 microns or in the 1.6 micron region, which means that these, if you apply the Boltzmann factor, you can realize that these lines will be much, much stronger and good probes of the chemical abundances in these stars. And yeah, so it's also the reason for being that the two different even parity levels are very close in energy here. So how do we get these atomic data? Well, there is the so-called golden technique for these transitions are the combination of two independent measurements. So the Einstein coefficient, the A value, or which is used in the absorption, the oscillator strength F value, that we get from two independent measurements. One is the relative intensities from the emission lines, which is called the branching fraction, and also the radiative lifetime of the upper level. They can be measured then separately. And if you look in optical and near-infrared regions, there is difficulties and advantages with all these. So if you have only optical lines, there will be a narrow spread in the branching fractions in terms of wavelength, which is good. And the lifetime will be in a 1 to 20 nanosecond range, which also is accessible for measurements. If you have both optical and near-infrared lines, the relative intensity will spread over a large wavelength range and will be quite hard to measure, whereas the lifetime is quite good. If you look at only near-infrared lines, levels with only near-infrared lines, the branching fraction spread will be narrow, which is nice, but then the lifetime will be 1 to 10 microseconds due to the scaling of the A value with wavelength. So this will be quite hard to measure. So you can see that if you have near-infrared transitions, they will either be hard to measure the branching fractions or the lifetime, which might cause some problems when you measure this, or some higher uncertainties. So our laboratory is called the Adlen laboratory. It hosts a FTS Bruker, which has a resolving power 10 to the 6, and it has a coverage of 4,000 angstroms out to 5 microns. The response in the optical region is rather low, though, so it can be used from, say, red into near. And as a light source, we have a hollow cathode, a double-sided hollow cathode, which is here is shown running yttrium, and then we can run the element we're interested in. The lifetime we have measured at the Lund High Power Laser Facility, which is soon introduced, and currently that's closed. And we currently use the calculations for lifetimes. And if someone wants to measure lifetime, this is highly encouraged by the community, because also the other major lifetime lab in Wisconsin-Madison has been closed. What the typical spectrum look like? So we get a very line-rich spectrum from these kind of cathodes. And you can see this goes from 5 microns out here to 1 micron here. So you get a lot of emission lines in the red region. You can also see the black body region from the cathode, and then all these lines. If we zoom in, you can see that the lines are very narrow. So they are Doppler. The Doppler width is approximately to 1,000 Kelvin. So the aim and the goal then is to measure the different line ratios here and calibrate these to the response of the whole system, and also the radiated transfer through the hollow cathode. And then we can also get from the line width and the line strength, we can get the parameters of the hollow cathode. The lifetime measurement we did at Lund Laser Center used a three laser system. So 2 lasers here, one when we just shown, and then a laser produced plasma, which was generated in this box over here. So basically, a rotating target of the element we want to study was illuminated by a neodymium JAG laser with a frequency of 10 Hertz. This produces a laser cone, and the laser cone was then perpendicular to the plasma, was illuminated by a laser which was shifted so it could excite the upper level. So two different lasers were employed, and in this case, so we can have this 1 nanosecond laser exciting this particular level of one to study, and then we look at the fluorescence in real time, producing a lifetime curve like this. So the dashed line is the laser pulse, the solid line is the measured data, and the cross is then the fluorescence. We can also apply a second step. So we have a first laser, and then a second laser, and then we can measure even parity level. And this was rather unique to the Lund Laser Center lab, because then we could access the next step of levels in this case. And this is the way it looks. So that you have the dashed line shows the laser pulse, and this is the fluorescence signal. And in the inset here, you can see the population of the state in between. So in this Another way to excite this even parity levels is by applying a very strong laser. Then we can get a 2-photon excitation directly without an intermediate step. So stacking 2 photons, we can excite these upper levels, like it's done here, for example, in chromium-2. So there is this technique. So we apply the experimental data, the FTS measurements combined with the lifetime data, combined with the theoretical data, this grasp calculations, and this can provide us with a good set, which we then can benchmark using the stellar spectra. So the stellar spectra, they work as both for benchmarking, but also to apply the data afterwards. And I will show 2 examples. This is the result for scandium, and this is the previous values that were used before, and this is our new log GFs on the x-axis. And you can see for the strong lines up here, it appears good, but for the weaker lines here, there's a good large scatter. And I should mention that this is a log scale, so then -3, so some of these values are off by 1 order of magnitude. And if you want to measure the chemical abundances to 5 or 10%, this is clearly too much. Here's the result for silicon, this is in private communication with Chris Needham. And the upper level, you can see there's a large scatter between all these points. But with our new data, the combined experimental and theoretical ones, all of these data for all these lines, one crosses one transition, brings down the value, and the uncertainty is quite low. I want to say another thing about the forbidden transitions. So we can apply the same technique to forbidden transitions, but then clearly the low transition rates, then the lifetimes are 8 orders of magnitude longer, and the lines are 8 orders of magnitude weaker in terms of A values. So we have to use clearly different techniques. And then we use the storage ring, in this case, the Desiree storage facility that Richard will speak more about in the next talk. So I will not mention it, but this is a unique storage ring that really can store ions under conditions that they can not decay by collisions, but will keep in the ring until they radiate. And we let also the astrophysical objects work for us. We don't apply the data to it, but we also let the mesh be the laboratory source for our branching fractions. So we use the spectroscopy of these objects to get the relative line intensities. So this is a picture from the Hubble Space Telescope. We just recently got accepted in a proposal for the James Webb Space Telescope to get more infrared data that we'll combine with these measurements of lifetimes. So this is what it looks like. These are the typical lines, and you can see by the brackets, all of these are forbidden lines. So I just highlight an experiment that we did last year, which with the Ulrich Berchins being the driver of this, for singly ionized barium. And there is a line at 2.0 microns, which we then could apply 2 different lasers. So we can empty the state, and we can, with a red laser, and we can also repump the state with the blue laser. So if we can transfer all the population to the ground state or to the excited state, and by this we could measure it really accurate. That's the range. So I apologize for the small plot here, but this is the result for barium, and we can then determine this lifetime to 1.5% accuracy, which is really excellent compared to the previous one, which has 15 or 20% accuracy. So by this, we can not only get the abundance and the excitation conditions of the stellar spectra and its nebulosities, but we could also test the calculations to really high accuracy. So we use the same technique for the branching fractions and the lifetimes for the 2 different sets, stellar stars, but also nebulosities.
Okay, you've got 1 minute left.
Yeah, thank you. And so I will finish off with this slide. So just summarize that the near-infrared atomic data is really crucial to meet the demands of the new observatories, both the ground-based and the space ones. And if we combine the calculation, the lab spectroscopy, we can get down uncertainties down to 5%. Thank you.